So, welcome. If you were wondering if you were in the right room, it is not about the SOS signal used for ships, but about a stochastic outlier selection algorithm. However, the base of the research was actually done in regards to maritime safety. So it had some hints from pirates of the high sea to those of high finance. I'll talk a little bit about an application within a financial context, but it can also be used in all kinds of anomaly detection scenarios. Normally, I don't start with a little frame about me, but this is the first time I'm speaking in Charleston, and I don't see any real faces that are very familiar, so I figured I'd introduce myself briefly. So I am working out of Winston-Salem, North Carolina. I do data science research. Been doing that for a few years, and for some reason I tend to gravitate toward anomaly detection, outliers, things of that nature, and hence why it's quite applicable to this conference this weekend. If you need to get a hold of me, Twitter is at @F_Dion, or my email, fdion@dionresearch. And a little bit more background. So I've been doing data science related projects for about 11 years or so. And really, initially, I didn't think there was a lot of future in that regard. It felt more like, oh well, it's yet another data mining approach, right? And then you start digging deeper and deeper, and the rabbit hole has no bottom. So this is a little bit about me, and this stochastic outlier selection algorithm came about because there was a problem, and the original problem was that you might not be familiar with that, but as far as, for example, in the case of Rotterdam, the port of Rotterdam, they have consoles where they're watching all the boats coming in, going out, and this repeats itself across the globe, right? I mean, you have the same thing you would have for airplanes. You need to have it for also boats. And although it might seem a lot simpler because we're pretty much on 2D versus a plane, you have the third dimension, there are other factors such as boats are going a lot slower than planes, so it's harder to detect minute changes and things like that, right? The other thing is these are human operators monitoring the maritime safety and security. They watch these large displays. So every so often, it's like, oh, nothing has changed. Okay, no, nothing has changed. Oh, no, nothing has changed. And so on and so forth. You can imagine how numbing the effect is, right? So turned out that their specific problem was kind of a universal problem when it comes to dashboarding views of security in general, right? I mean, the moment you start looking at a screen that looks the same day in, day out, you just zone out. And it says, despite the visual aid, anomalies often remain undetected. So this is not teaching you how to become a data scientist. I'm just briefly explaining a little bit these terms. So regression, if you, for example, think of, oh, I want to know how much I should pay for a house. So you'll do your research, right, and figure out by the square footage and things like that. What you're doing without knowing it is you're doing regression, basically. You're trying to figure out, given a set of data, what is the predicted price for a house with different characteristics, right? Classification is a little different, but it's equally something we do fairly often. For example, if I bring up, let's say, a Blu-ray and a cassette, right? I mean, obviously, there's not a lot in common. The only thing is it starts Star Wars and Star Trek. So it starts with star on the name of whatever is on there, right? But beyond that, how do you know, do I classify these things as similar? This is text. This is an episode being narrated. This is a movie. Are they similar? So this sounds like a pretty simple thing to do. But when you start having different things, oh, this is a VHS tape. So now it is Star Wars also. So these are probably should be classified as the same thing, but they're on different media. So when you start adding all of these things together, it gets a little confusing as to what is considered a class, right? Just briefly. So clustering is similar to classification, but basically you're saying, here's all the stuff I got, and algorithm, figure it out. What are things that go together well based on what type of algorithm in particular. So for example, it might be the nearest neighbor calculation or stuff like that. You can specify also in certain algorithms how many clusters you're expecting to see, and it will try to figure out and cluster the data. And that's pretty useful on its own. But clustering, one issue is that it goes quickly when you add features and you're trying to represent that in a form, a visual form that you and I can understand. You need to see that in a two-dimensional, maybe three-dimensional space, but beyond that, it would be fairly difficult to really visualize all these clusters in n dimensions, where n is maybe 1,000 or something like that. So the next one helps us with that. It's dimensionality reduction. And so when you have too many features, you can actually try to figure out how you can eliminate some, or you can also actually go into dimensionality reduction, where you will map these features back to maybe 2D. And we'll show an example of that. And anomaly detection, and that's basically what we'll be mostly focusing on today. As far as anomaly detection, we do that naturally. We know kind of this does not belong, or this doesn't feel right, or I mean, might be laying down in the bed and we hear a noise. It's like, oh, hey, what was that? Or so I mean, it's something that naturally we are able to do. But of course, if we can automate these things and be really good at it, then it alleviates the pressure on the human to perform day in and day out, watching a display, trying to figure out what's going on, right? There's no perfect algorithm in any of these things, right? I mean, these are just models or estimation of reality, and sometimes they are very wrong. But as long as they're not completely wrong, as long as they are, you know, right enough to serve our purpose, they're okay. So, and that's basically what we'll see. And if you are really into learning more about anomaly detection, I have a podcast on artchive.es. So art, ARTCHIV.es, archives. Yes, all right. Not that easy to remember, but we will not cover any of these other things. These are all bread and butter data science things, but such as feature engineering and ensemble methods, or deep learning, or decision trees. We just don't have the time to cover any of these things, but they can be incorporated in anomaly detection too, or alongside anomaly detection. I will use the Jupyter Notebook environment, and if you've never seen that, it's actually quite useful also for doing various information security related things. I mean, basically it documents all the steps. There's a version of Jupyter Notebook that allow you, for example, to run bash commands. So if you're an expert in bash, then you can actually also document that, integrate your graphs, charts, and text within the notebook environment. And at the end, you have a report that can be used also. Behind all of that is Python, the programming language. Scikit-learn will use it only just for something called tsni, T-distributed stochastic neighbor embedding, and that's related to SOS also. Of course, pandas is how we can load data and have it in a nice tabular format in memory so we can do the manipulations. So I mentioned SOS, but what is SOS? So it's an affinity-based outlier selection with a probability score. Wow, that sounds like too much, right? So affinity-based. So first of all, what is affinity? Again, going back to my different things. Anybody knows what that is? No? 8-track. Okay. What's on it is actually somebody did a home recording of a Star Wars episode, which I thought was kind of weird. But anyway, I ran into that. So again, this is Star Wars also on magnetic tape. So they have an affinity because they are related to the same subject and are on the same media as far as features, right? But this is audio and this is video. So this is where they start diverging. So if I bring back this, would you say that these two have more affinity or these two have more affinity? So this? Possibly. So again, it depends how many features you have. How you define that? Yes, exactly. So that's the thing. To define affinity, we actually have to define a step before that, which is a dissimilarity metric. How not related two things are, which is kind of like, what? Why do we need to do that? Well, because that allows us to make it a nice symmetrical matrix, which we can then transform into an asymmetric affinity matrix. And I'm not going to go into the detail of that. I mean, there's a 209-page PhD thesis just on that, so this is beyond the subject. And by the way, I didn't write any of that. That's Joran Jansen, who I credited at the beginning and toward the end also. So this affinity also has been used for clustering in the case of affinity propagation, and for dimensionality reduction, which would be SNE or tsni, which are visual techniques for, I mean, it's not visual, it's basically allows you to reduce your large feature space into something that can be visualized easily by using two-dimension, or actually to be able to be modeled more easily, because the more features you have, it can be a challenge sometimes to model these things, right? The algorithm, we're not going to go through it. It's, yes, a lot of text. But we can go through it visually. And that's what I was kind of hinting at. Here we have 6 data points. 1, 2, 3, 4, 5, 6. These could be network packets. These could be bank transactions. These could be, I mean, you name it. Or they could be the features of this tape as far as the coercivity of the magnetic material, or I mean, who knows what could be useful, right? But we have to define these things. So once we have these, in this case, it's just 2 features. These 2 features, though, are going to be combined because as a representation of just item 1. Item 1 is then going to be compared to itself, which means that it's not dissimilar at all. It's completely the same, but we actually don't want that. We just ignore because you can't really, I mean, it doesn't bring you anything to compare something with itself. So we just skip those. And then we'll compare it with 2, 3, 4, 5, and 6. And 6 is very green, so that means it's more dissimilar than anything else with 1. And we repeat that. Now, imagine the challenge here is that if we have 6 elements, we have to have 6 by 6 data points. now in the matrix, right? I mean, if you add 1,000,000, that means you have 1,000,000 by 1,000,000. This is getting quickly untractable from that perspective, right? Unless you have, you know, an infinity of memory. So at some point you have to start looking at how much time period I want to look at, and also how much data do I really want to look at once, and can I partition that naturally so I can distribute it across a computing cluster. So,
can I ask you a quick question?
Sure.
So couldn't this be symmetric, like, you know, the similarity of I with J could be the same of the
Yes, 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 yes. So you only have to do half of the calculations here. Yes, because, well, let me rephrase that. Assuming we're looking at the, like in this case, a distance metric Euclidean space, for example, or something like that, that's true. So meaning, what I mean by a Euclidean space is that if I have this guy here, and this guy here, physically, this guy is the outlier. This is the dissimilar thing. Not looking at anything else. I decided that my metric is going to be the distance between the points. For boats, that might be very useful. For other things, might not be as good. But yes, it is symmetrical in the case of an Euclidean distance. The affinity itself, though, is not. So that's a little bit different. And so that's where a lot of the work was done on that research, is how to go from that dissimilarity to that affinity. And then binding probability. So for each of these, how likely am I to be a neighbor of this other data point? And so that's basically it, but that's not useful in the matrix form for us. What we need in the end is the outlier probability. So in this case, and that's as much theory as we will cover. After that, it'll be a lot more interactive. But so we convert basically these probabilities, probability matrix, into outlier probability for each data point. So we end up with 6 values, each ranging between 0 and 1. And 0.5 is an arbitrary decision that anything above 0.5 would be an outlier or an anomaly, and anything below. Of course, this can be adjusted, and you know, if we decide that we want to not have it unsupervised, but we want to supervise it at a higher level. In this case, laser pointer, it's showing this guy as dark red, which wouldn't put it over here. So it's very likely that this is an outlier. And visually, we can, fortunately, it's a fairly simple example. We can definitely see that, yeah, this guy is an anomaly compared to all the other data points, right? But it's not always like that. So I did use this in conjunction with other techniques, made a hybrid system where there's voting involved and things like that, in order to identify outliers, or I can't really go into the detail, but for financial data. The one thing that you will learn, and you've learned already if you've been doing information security for a while, is that the data that somebody gives you that is supposedly clean and incredibly accurate usually is not. There's missing values, there are errors, there's indexing issues, there are all kinds of stuff, right? So the raw data itself probably doesn't work out of the box. You have to start looking into it. So you'll have to do maybe cleaning the data. You might have to engineer new features, meaning that I'm going to combine different features. Like, for example, if it was in network security, maybe I would expect a specific request to always have an answer or something like that, and I could say didn't get an answer, that's a new flag, that's going to be a feature, right? And sometimes we just have too many features, we just got to drill down and reduce the number of features. Everybody following up to now? Yes, good. All right. The other aspect is, well, my first thought is, well, I really need to flag anything that looks vaguely suspicious as an anomaly, right? Well, each outlier or each anomaly that you bring up to somebody, they are now obligated to research it. They have to go through and figure out, was this fraud, was this whatever. I mean, actually, they don't even care about the intent. Was this, did something happen here, right? So, you cry wolf too many times. Hence, by itself, SOS, unsupervised, is a little too trigger happy to label stuff as outliers, right? So that's where a hybrid system is probably needed to really do a better job. At the end of the day, though, you really want a human that can go through and bulk select and say, no, this is just normal business, right? And as I mentioned, SOS is but one of many outlier selection algorithm. And again, ensembles, so when you have multiple algorithms trying to tag something, if I have 5 algorithms, 3 of them flag something as an outlier, there's probably a good chance that it is. Or even better, if, like SOS, they assign not only an outlier or not outlier, they give me a probability, then I can actually use these probabilities in the voting mechanism that's a little more advanced also. So in order to use that, there's a lot of installation that needs to happen. However, if you download, there's something called Anaconda. I don't know if you've heard of it. But basically, you can download Anaconda, anaconda.org, I think is the website probably, if it's not anaconda.com. And basically, it allows you to install not just Python. It comes with the Jupyter Notebook. It comes with Pandas and scikit-learn. The only thing you'll have to manually install is scikit-SOS, which I'll show here. So I would do a pip install. Once Python is installed through Anaconda or by hand, pip install scikit-SOS. And, well, in this case, I had already installed it, so it says, says already installed, so it doesn't need to reinstall it. So that's the installation. So from the command line, we can actually use SOS. Once it is installed, it doesn't do anything like this because it's expecting me to pipe data to it. So I think, yes, so I did already grab from the UCI machine learning public data that they have. They have some different data sets, and one about computers. That's actually from the 80s, so you won't recognize the brand probably. But if I copy that, so basically it went and gave me the probability. I could also have.
So these probabilities mean that how high is it the probability for it to be an outlier and therefore maybe an attack, something abnormal?
Yeah.
So that 51 could be something to look into.
Yeah, it's pretty close, or 56. But in certain cases, depending on your features, you might see a lot of 0.9 or things like that. So, but anyway, it can be used at the command line, but really for this demo and for general use, it's probably best to use it. So the same set here through a Jupyter Notebook already set up, so I don't have to type and spend too much time on this. So I'm going to read this data, and the first thing I look is that there's no header, which that's always disappointing. I transposed it so the header would be here, just so I showed the first 5 records and we could read it on the screen. But yeah, no header, so I don't know what these represent, so that's not that great. So let's read it this time with header. So when I'm saying, you might have to do some work before you can actually use the data, that might be some of the things like trying to figure out what data do I have. Okay, what are all these logs? Are these like a web log? Is it configured in a standard fashion, or is that somebody that decided that they wanted things in a different order, different data fields, and things like that? So these, yeah, I mean, it doesn't need some work from that perspective. Aha, now I have all very popular computer brands, right? The Advisor, Amdahl, no. Okay, these are kind of old. But what was interesting about this data set is that it had basically the published performance, and they were using that to test regression, to guess they were estimating the performance of a machine based on a few very simple things. The cycle time in nanosecond, the RAM, and the cache. So basically, if you think of a computer that's nowadays is probably not as interesting to just know these things, because performance is impacted by a bunch of different things. But in 1987, that was the case. So you could do that. So what does SOS does with that? So I could initially say, okay, give me all the data, all the fields. So I'm running, my detector is SOS, and let's see if it can run it. Oh, I got an error. Can't multiply sequence by non-integer of type string. So what happened is that I had the brand, like Amdahl, that's a string. I mean, it doesn't know anything about that, right? I mean, it's not a number that I can put in a matrix and multiply. So that's not going to fly. And that's one of the challenge with feature engineering is if you have any strings, let's say you have it's a verb, like a HTTP verb or something like that, like get or post or put or things like that, or the type of packet or whatever. And these are categorical data. It's not just a number. So you have to convert them into a number before SOS can actually use it. So here is what I'm doing with pandas. And I will post these things on GitHub. So just, again, I posted my email, just drop me an email. But if you look at github.com/fdion, I got already a bunch of different things there. I will eventually post this when I get home. So I'm converting the vendor and the model to category codes. I'm rerunning the prediction, and now this time it worked. Let's see what's the output. Okay, scores. Oh, I haven't assigned the scores yet. So, yeah, I did. Let's see. Yes, our scores are right there. So imagine these were packets, and we'll look at the next notebook will be actual from a network capture. But here we see these scores, and I said just anything that's greater than 0.5, which means it's an anomaly. I could have also said just sort them descending, which is really ascending equal false. And now it shows that the Burroughs and Amdahl machines are at the top of the anomaly based on their spec compared to the performance. And so we're wondering, so what does that really represent? And really, because I didn't do any job of selecting my features, I'm actually, getting probably garbage here. Because I would have to select only the fields that I really need. Like if I were to redo this and just selecting these fields, like the machine cycle, the maximum RAM, the cache, and the maximum channel, let's say, then I can actually see that my results are different. a VAX machine is now at the top of my outliers. So you see how sensitive to the features this as it's trying to figure out the affinity between the data fields. If you have too much data, at some point you get the noise is actually what's fitting the model, right? So that's where you have to be really careful as to what you select. Now, let's see if we can visualize this. I said that SOS was related to t-SNE. t-SNE is a dimensionality reduction. So I'm going to reduce that data set to just 2 dimension. And I'm transforming it into the 2 dimension. I'm going to assign this to X and Y. And I'm going to use a plot to display. Now, this is interesting because it's definitely grouping different sets of data in different ways, as you can see. So now, I mean, if you, instead, this is a static graph, but if you use an interactive graph, then you could actually hover and see what the individual data points are and things like that. So you can actually help a hybrid system with a human interaction to review some of these things. And then you could color code that based on your probability that you've assigned through SOS. And now you're really gaining a lot of knowledge from your data set from if you're looking at anomalies or not. Let's look at the other example briefly. Network packets. This is recent, 2017, from the same UCI repo, which is a pretty common repo for testing machine learning algorithm. Now here, I'm going to read this. Actually, I'm going to click on the link. So the data is the burst header packet flooding attack on optical burst switching network data set. And there's a bit of information as to what the fields are, why they were selected, and the research also, the paper that's tied to that. So this is more your typical InfoSec type of work. And again, we can just use, we can read the file. Well, can read the file if we are looking in the right place. Okay. So now we're looking. So we'll have the node number, the bandwidth rate, the packet drop rate, the full bandwidth for that. I mean, you see there's a lot of attributes that are available. Again, we would have to do our due diligence to figure out what are the features that are really important for us, or are there features that are missing? And then that's where you actually have to spend some time trying to figure out, oh, well, I need a temporal thing, maybe. I need to figure out how much time has it been since I've seen such a low rate for that node, or things like that. Is that a normal cycle that's happening? This could be a flag as another feature. But without that, we'll just assume that the bandwidth rate, the packet drop rate, the full bandwidth, and the percent loss packet in terms of rate and bytes, and the received rate also is what we want to look at. And now what we'll see, okay, what we'll see, running SOS again, the detector predict, it ran pretty quickly. So now we're assigning the score. If we look at the score, greater than 0.5, what is interesting, I'm going to look at the last column where this data set actually had been classified manually. So it shows blocks. So these were blocking the traffic there. And all of these that have very high probability of being outliers are all tied to packets that were malicious, actually. So that's kind of cool. I spent only a few minutes with the data set and it just spit that out. However, obviously there are suspicious packets that we didn't catch. that are not even showing as being outliers. And that, of course, if you have a flooding event that's pretty intense, your anomaly might be the normal to a certain extent. So again, you got to keep that in mind. But if you have multiple detectors and you combine them in a voting algorithm, then you'll get closer to reality here. So again, these will be available, but let's go back to our presentation. We did the notebook demonstration. Best practices. So don't boil the ocean, start small, take a very small data set, just try to work it through, figure out, is it working for something I really know, that I've already done the work, I've labeled things as being, okay, this is an outlier, this is definitely an attack, or whatever you're looking at. Also eliminate the features that are not really helping. Sometimes you actually, for example, if I add the speed of your car in miles per hour and kilometers per hour, that's useless information. Yes?
So how do you do your feature selection? Are you using PCA? Because feature selection is the art and the science and what really affects these algorithms.
Yes, yes.
So do you have some pointers, or what you consider as a best practice?
I didn't mention, I wouldn't cover that, but just briefly, I'll say that yes, it is very difficult. I mean, like I've been doing this for about 11 years, as I said, and so you kind of start getting a feel for what's important. The other thing is you have to have good tools that will measure some metrics. So you can actually look at the quality of the data. I did an assignment recently where they assumed the quality of the data was at this level. It turned out to be a little bit lower than even for very critical data fields. So if you don't have any way to measure that, you don't know the features that are very poor quality, you don't want to use them, obviously. Or maybe you can get a different source to gain the same information. But eliminating features is yes, a challenge. That's where you could use something like TSNE, as I was showing, which is similar to using PCA also. Or, I mean, there's about a dozen or so techniques for doing that. The best, though, is to try to figure out how combination of, particularly if you have data where you know the actual results, you can actually go and look how each of these features, not just individually, but as groups, also impact your results. And there are some statistical techniques, but I mean, if you want, we can talk about that later. But there are ways to actually select features that are more important, and you always want to start with those. And then you'll see if you have a tiny incremental gain adding more features. Scikit-learn has some of these things built in, the feature elimination or feature selection. It also has pipelines. So pipelines are your automation for these kinds of problems, just like Ansible would be for DevOps work, or as we learned today, maybe also for orchestrating attacks on large networks. But yeah, so that's the equivalent. These are pipelines, part of scikit-learn. Also, think of your data as something, particularly for networks, right, as a temporal data. So if you look at, if you have, I don't know, if you have enough traffic that 1 hour has all the data you need to find outliers, then you can start with that, and then just have a window that constantly look at 1 hour of previous data up to now, and see what sticks out, or something like that. That way you don't have to scale on really expensive hardware or cloud services. And yeah, as much RAM and as fast as a CPU as you can afford. It's time that you save during these different processing. I used very small examples, but when you start talking about hundreds of thousands of records that you want to process and try to find an outlier at once, then you end up again with that problem where in X and Y of that matrix, you have 100,000+ records, right? So, and you have to basically compare each data point with every other data point. If you do need to scale beyond, very fast servers or whatever, you can actually have multiple servers, and there's a Spark implementation, if anybody familiar with Spark. So mostly for big data processing, but in this case, it's just we need a ton of RAM. We need a lot of RAM, so it's not that it's big data, it's just expensive to run. So Spark, if you search on GitHub for stochastic outlier selection, beside the Juran Jansen's implementation for scikit, there's a Spark implementation also out there. And so, with that, we are exactly on the questions. Anybody has a question? Yes.
I have a lot of questions.
Okay.
But about the stochastic outlier selection, how is this better than? And I'm not doubting that it's better. I really like the idea and all that. I just want to see how it can improve my classification compared to the standard k-means. That still there is an outlier.
Mm-hmm. So, in fact, so this is the second edition of Agarwal outlier analysis on Springer, and he doesn't mention SOS here, as far as I know. I just upgraded from his first edition, so yes, it's relatively new. But if you look at Jensen's thesis, he goes and compares to other algorithms and how well they work. So TSNE also, if I go back actually, let's see. So I will post that, but like affinity propagation has been used, like I mentioned, for clustering by Fry and Duke, but also Hinton. I'm sure if you've heard anything about deep learning, you've heard that name before. So he developed SNE, and Van der Matten continued that work to do the TSNE. So these are actually, again, fairly expensive. Affinity, anything that's pairwise comparison where you have to compare one element with every other element is always expensive. But that's definitely the gold standard from a perspective of that without taking any shortcuts, right? So again, you've got to measure, do I have enough time to do this? If not, are there other techniques? And as I mentioned, it might be that you need a set of 5 different algorithms to really identify with enough confidence your data. Particularly if your data is not labeled in any way, then you're going to have to look at every single specimen that is flagged as anomalous, right? So yes.
I was wondering if you might be able to further explain how it scales, how as you add subjects versus as you add
Features.
Features.
Yes. So in the case of features, I did say, selection, try to reduce the features. It has a lot less impact than the actual number of data point in terms of memory usage, but you still have to do a bunch of calculations, obviously, to reduce that into your dissimilarity matrix, right? And the dissimilarity matrix is in the GitHub version is hardwired to be a Euclidean distance, but there's nothing that prevents you from using any other type of similarity metric or dissimilarity metric, basically. So that will also play a role into the effect of the features. But yes, I mean, to answer your question, features less expensive, number of data points more expensive in terms of scaling that.
Linear versus exponential?
Well, I mean, basically, you have to multiply whatever number of feature by itself. I mean, I'm sorry, number of data point by itself, and that's the size of your matrix. So, you know, it's the square, right? So, all right. And again, if you have, if you want to download these things, pretty easily available. I'm seeing a lot more notebooks being released also for information security in general. So you'll want to check those out. And again, my contact info right here, and the credits for the different illustrations and the video and stuff like that. Yes.
Redoing this talk at the Python users group?
Yes, I believe I will. So. Yeah, so I'm actually, I organize a Python user group in Winston-Salem in North Carolina. So if you're, I might actually do it in Charlotte too. I don't know, anybody from Charlotte around there? Yeah, a few. So, and might have different examples also. So, yeah. All right. And, well, that's pretty much it then, I guess. Thanks.